Voltage buildup on a 3-step platform near an SF6 breaker in a high-voltage switchyard can stem from several factors. The most common reasons relate to grounding problems, insulation issues, and electromagnetic induction. Let's explore these possible causes. Firstly, consider grounding issues. The platform might not be properly grounded, especially at the end opposite the grounding connection. This creates a potential difference between the platform and the substation ground. The grounding conductor itself could be corroded or damaged, thereby reducing its conductivity and hindering proper grounding. A faulty ground connection is a primary suspect in these situations. Secondly, examine the electrical isolation of the platform. The platform may not be adequately electrically isolated from the exposed overhead buses. Damaged or loose insulators can allow electrical current to flow through the platform, leading to voltage accumulation. The integrity of the insulators is crucial to prevent unwanted current paths. Thirdly, induced voltage from the buses is a significant factor. The overhead buses carry high voltage electricity, and this can induce a current in the platform through electromagnetic coupling. If the platform is not grounded effectively, the induced current can build up, creating a voltage potential. The effectiveness of the grounding system directly impacts how well induced currents are managed. Fourthly, resonance effects could be at play. The platform and the overhead buses may form a resonance circuit. At certain frequencies, the induced current can resonate with the inductance and capacitance of the platform, amplifying the voltage buildup. This is particularly relevant if the system operates near a resonant frequency. Fifthly, electrostatic charge accumulation can contribute. The platform may accumulate electrostatic charge from wind, dust, or other environmental factors. If the charge is not dissipated properly, it can create a voltage potential. Proper grounding helps to dissipate these charges. Sixthly, the design of the grounding system itself is critical. The grounding system design may not be adequate to handle the induced currents and electrostatic charges. Incorrect grounding connections or inappropriate grounding materials can increase the risk of voltage accumulation. Ensuring that the grounding system meets the specific requirements of the switchyard is essential. Finally, other factors should be considered. Stray currents from nearby equipment or sources can contribute to the voltage buildup. Maintenance or operational errors that have compromised the platform's grounding or isolation are also potential causes. A thorough investigation should consider all these possibilities. To further elaborate on grounding issues, it's important to understand that grounding isn't just about connecting to the earth. It's about providing a low impedance path for fault currents and induced currents to safely dissipate. The grounding conductor must be sized appropriately to handle the expected fault currents, in accordance with standards such as IE80. If the conductor is undersized, it can create a significant voltage drop along its length, effectively raising the potential of the platform relative to ground. The material of the grounding conductor also matters. Copper is generally preferred for its high conductivity and resistance to corrosion. However, in certain environments, copper can corrode, especially if it's in contact with dissimilar metals. Regular inspection and maintenance of the grounding conductor are essential to ensure its integrity. The connections to the grounding conductor must also be secure and corrosion resistant. Loose connections or corroded connections can significantly increase the impedance of the grounding path, negating the benefits of a properly sized conductor. In addition to the grounding conductor itself, the grounding grid plays a crucial role in equalizing potential differences across the switchyard. The grounding grid consists of a network of interconnected conductors buried in the earth. The purpose of the grounding grid is to provide a low impedance path for fault currents to return to the source, minimizing the risk of step and touch potentials. Step potential is the voltage difference between 2 points on the ground that a person could touch with their feet. Touch potential is the voltage difference between a grounded object and a point on the ground that a person could touch simultaneously. The grounding grid is designed to minimize these potential differences, ensuring the safety of personnel working in the switchyard. The design of the grounding grid must take into account the soil resistivity, which is a measure of how well the soil conducts electricity. Soil resistivity varies depending on the type of soil, its moisture content, and its temperature. In areas with high soil resistivity, it may be necessary to install ground rods or use chemical treatments to lower the resistance of the grounding grid. Moving on to electrical isolation faults, insulators are critical components in a high-voltage switchyard. Their purpose is to prevent current from flowing where it's not intended, such as through the platform. Insulators can be made from a variety of materials, including porcelain, glass, and polymer. Each material has its own advantages and disadvantages in terms of dielectric strength, mechanical strength, and resistance to environmental factors. Over time, insulators can degrade due to exposure to ultraviolet radiation, pollution, and mechanical stress. This degradation can lead to a reduction in their dielectric strength, increasing the risk of flashover. Flashover is an electrical discharge that occurs across the surface of an insulator. Flashover can damage the insulator and can also create a hazard for personnel working in the switchyard. Regular inspection of insulators is essential to detect signs of degradation. This includes looking for cracks, chips, and surface contamination. Insulators should be cleaned periodically to remove dirt and pollutants that can reduce their dielectric strength. In some cases, it may be necessary to replace insulators that are severely degraded. The installation of insulators must also be done carefully to ensure that they are properly aligned and that there are no sharp edges or protrusions that could create a point of high electric field stress. Corona discharge, a localized electrical discharge that occurs around conductors at high voltage, can also damage insulators over time. Corona discharge is caused by the ionization of air around the conductor. The ionized air can react with the insulator material, causing it to degrade. Corona rings are often used to reduce the electric field stress around conductors, minimizing the risk of corona discharge. Addressing induced voltage from buses, electromagnetic induction is a fundamental principle of electromagnetism. When a conductor is placed in a changing magnetic field, a voltage is induced in the conductor. The magnitude of the induced voltage is proportional to the rate of change of the magnetic field and the length of the conductor. In a high-voltage switchyard, the overhead buses create a strong magnetic field. This magnetic field can induce a voltage in the platform, even if the platform is not directly connected to the buses. The amount of induced voltage depends on the geometry of the platform and the buses, the voltage of the buses, and the frequency of the current flowing in the buses. The induced voltage can be reduced by shielding the platform or by increasing the distance between the platform and the buses. Grounding the platform is also an effective way to mitigate the effects of induced voltage. When the platform is grounded, the induced current flows to ground, preventing a voltage buildup on the platform. However, it's important to ensure that the grounding system is adequate to handle the induced current. If the grounding impedance is too high, a significant voltage can still develop on the platform. Resonance is another important consideration. Resonance occurs when the inductive reactance and capacitive reactance of a circuit are equal. At resonance, the impedance of the circuit is at a minimum and the current is at a maximum. In the case of the platform and the overhead buses, the platform can act as an inductor, and the capacitance between the platform and the buses can act as a capacitor. If the frequency of the current in the buses is close to the resonant frequency of the platform, a large voltage can develop on the platform. The resonant frequency depends on the inductance and capacitance of the platform, which in turn depend on the geometry of the platform and the buses. The resonant frequency can be shifted by changing the geometry of the platform or by adding additional inductance or capacitance to the circuit. Damping resistors can also be used to reduce the amplitude of the resonance. Electrostatic charge accumulation is another potential cause of voltage buildup. Electrostatic charge can accumulate on the platform due to a variety of factors, including friction, induction, and the triboelectric effect. The triboelectric effect is the phenomenon of charge separation that occurs when two different materials are brought into contact and then separated. The amount of electrostatic charge that accumulates on the platform depends on the material of the platform, the humidity of the air, and the amount of friction or contact with other materials. Electrostatic charge can be dissipated by grounding the platform. When the platform is grounded, the electrostatic charge flows to ground, preventing a voltage buildup on the platform. Static dissipative materials can also be used to reduce the accumulation of electrostatic charge. These materials have a low surface resistivity, allowing charge to flow easily across their surface. The grounding system design is paramount. The grounding system should be designed to provide a low impedance path for fault currents, induced currents, and electrostatic charges. The grounding system should also be designed to minimize step and touch potentials. The design of the grounding system should take into account the soil resistivity, the expected fault currents, and the geometry of the switchyard. The grounding system should be inspected regularly to ensure that it is in good condition. Ground connections should be checked for corrosion and tightness. Ground conductors should be checked for damage. The grounding grid should be tested to ensure that its resistance is within acceptable limits. Stray currents can also contribute to voltage buildup. Stray currents are unwanted currents that flow through unintended paths. Stray currents can be caused by a variety of factors, including unbalanced loads, faulty equipment, and improper grounding. Stray currents can create a voltage drop in the grounding system, raising the potential of the platform relative to ground. Straight currents can be detected by measuring the current flowing in the grounding conductors. If stray currents are detected, the source of the current should be identified and corrected. Maintenance and operational errors can also lead to voltage buildup. For example, if a ground connection is accidentally disconnected, the platform may no longer be properly grounded, leading to a voltage buildup. Similarly, if an insulator is damaged during maintenance, the platform may no longer be electrically isolated from the buses, leading to a voltage buildup. It's important to follow proper procedures during maintenance and operation to avoid compromising the platform's grounding or isolation. All work on the platform should be performed by qualified personnel who are familiar with the hazards of high-voltage electricity. In summary, voltage buildup on a 3-step platform near an SF6 breaker in a high-voltage switchyard is a complex issue that can be caused by a variety of factors. A thorough investigation should consider all of these possibilities, including grounding issues, electrical isolation faults, induced voltage resonance, electrostatic charge accumulation, grounding system design, stray currents, and maintenance or operational errors. Proper grounding is essential to prevent voltage buildup and to ensure the safety of personnel working in the switchyard. Regular inspection and maintenance of the grounding system, insulators, and other equipment are also crucial.